Okay, let's look at some of these past paper Matric questions on basically on forces and on Newton's laws. It's forces, Newton's laws, and there's sometimes small momentum things that are linked to it based on the two definitions. They come from all the Matric past papers from 2014 onwards. So the first one says, which one of the following physical quantities is a measure of the inertia of a body? This one's easy. The answer is A. In the grade 12 guidelines, there's no definition of inertia, but it is in the grade 11 guidelines that a measure of the inertia of a body is your mass, how many particles you contain. The second question here, this is based on this law, Newton's law of universal gravitation. So it says the magnitude of the gravitational force exerted by one body on another body is F when the distance between the centers of the bodies is doubled. Okay, now this is an inverse square law. So if R gets big, then the force gets small. Okay, so the bigger the distance, the smaller the force. And it says, so what will happen now if the distance between the centers is doubled? Well, first of all, we're going to cross off everything that is bigger than F. So there goes C and D. But if the distance between the center of the bodies is doubled, we are now dividing by 2R all squared, which means we are now dividing by 1/4R squared. So the answer is going to be a quarter of the force. Now it says two forces F1 and F2 are applied on a crate lying on a frictional horizontal surface as shown in the diagram below. F1 is bigger than F2. So what's going to happen here? If I have one force that is bigger than another force, I will have a net force. And if the force F1, which is going west, is bigger than the force F2, I'm going to have a net force to the west, and according to Newton's second law, the object will accelerate in the direction of the net force. So the answer is going to be B, accelerate towards the west. You can't be moving at a constant speed because anything that's moving at a constant speed is in equilibrium, and if you are in equilibrium, your net force is 0. So now if we have a look here, we are now looking at 1.4 here in my list. A person stands on a bathroom scale that is calibrated in newtons in a stationary elevator. The reading on the bathroom scale is W. The elevator now moves with a constant upward acceleration of 1/4 g, where g is the gravitational acceleration. What will the reading on the bathroom scale be now? Okay, so when we are in a stationary elevator, the force upwards and the force downwards are balanced and there's no net force, okay? If you are moving upwards, then there is a bigger upwards force than there is a downwards if we are accelerating upwards. So in these questions, sometimes it's hard to think about what's going on, okay? But what happens is, if you imagine yourself in a lift that suddenly goes upwards, you can feel the floor pushing really hard on your feet and you feel like heavy. Whereas when the lift accelerates downwards, the floor like kind of drops out under your feet and your stomach goes all wibbly wobbly and floats up into your mouth, okay? So I always think about these questions without thinking about the physics too much, and then I say, okay, if the elevator's going upwards, I'm going to feel heavier, okay? And that gives you 1.25 times your weight. But what's actually happening is that what is the scale reading equivalent to? The scale reading is kind of equivalent to the normal force on the scale. And if you've got this situation here where this is 1.25 g and then there's only mg downwards, then your normal force is actually bigger than the force going downwards, and then you get a larger weight. So I just usually go and think, okay, what's going on? When the lift goes up, I feel everything sinking down into my feet, and I feel really heavy, like it's hard to lift my feet, and therefore my weight is going to be bigger. So I know that's not the best answer, but that's how it works for me, and I always end up with the right answer. So the next question, 1.5, the simplified diagram below shows a rocket that has been fired horizontally, accelerating to the west. So there is a net force to the west. Which one of the statements below best explains why the rocket accelerates? So if you have a look here, the exhaust gases are going that way and the rocket is going that way. So what is happening is the rocket is producing exhaust gases that go to the east, okay? And when the exhaust gases go to the east, according to Newton's third law, there's an equal and opposite reaction, and the rocket will, well, we can't say that because we're not allowed to, but everybody remembers it that way. There is a force of equal magnitude and oppositely directed, so then the rocket goes to the east and the gases go to the west. Did I read that correctly? Yes, the gases are east and the rocket is west. Remember, when you do anything with Newton's third law, the two sentences must contain exactly the same words. So we've got the rocket and the exhaust gases, and then the exhaust gases and the rocket. So you put you put the first sentence, and then you swap the order of the two objects in the sentence, because it's always a pair of objects with Newton's third law. Now it says 1.6, the tendency of an object to remain at rest or continuous uniform motion in a straight line. Well, it's definitely not Newton's third law, because that's the equal and opposite law. It's not the second law, because that's the acceleration. And if you are having a uniform motion, you are most certainly not accelerating. You're traveling at constant velocity. So it comes down to the grade 11 definition of inertia, the resistance of an object to any change in its state of motion. So if it says if you remain at rest or continue uniform motion in a straight line, then you are resisting changing your motion. Okay, now it says to you the mass of an astronaut on Earth is m. At a height equal to twice the radius of Earth, the mass of the astronaut will be. Now usually when you see these questions, you start with F equals G m1 m2 over r squared. And when we look at these, the F is in fact your weight. Now, has this question anywhere mentioned your weight? It has not. It says mass. It says mass. How would you change the mass of the astronaut? You would have to chop off some particles in his body, like cut his head off, cut his arm off, cut his leg off. They are not doing that to the poor astronaut, so his mass must be exactly the same in space as it is on Earth. It is only his weight that is different, because mass and weight in physics are not the same. The acceleration due to gravity on Earth is greater than that on the Moon. Which one of the following statements is correct? So remember, the acceleration due to gravity, it's little g, and your weight is equal to your mass, the number of particles in your body, times little g. So the weight of an object on Earth is the same as that on the Moon. No, it's not. Mass and weight are not the same. Only the mass is the same on the Moon. The mass of the object is the same as that on the Moon. That looks promising, number B. The mass of an object on Earth is greater than that of the Moon. No, mass and weight are not the same. Then number D, the weight of an object on Earth is less than that of the Moon. No, that one is wrong, because if G is bigger on Earth, then W is bigger on Earth, and the mass stays the same. The force diagram below shows the forces acting on a box. Which one of the following equations for the magnitude of the normal force is correct? So we assume that this box is vertically in equilibrium, okay, because it's not flying up into the sky, it's not accelerating upwards. So if we say up is positive for this box, and we draw a little force diagram, we've got the normal, we've got the weight, and that does not look like an N, the normal, the weight, and then we've got this applied force over here. So now obviously these forces are not in a straight line, so if we want to consider them, we must put them in a straight line. There's the weight going down, there's the normal going up, there's an X component of F, and there is, which I'm struggling to draw in here, a Y component. Okay, so if we look vertically and say up is positive, the N plus that force we're attaching, the Y component of the force, minus the weight is equal to 0. So what would be the normal? The normal will be the weight minus Fy, and Fy should be, I do believe, our friend sine. So the answer should be D, the weight minus F sine theta, because cos theta is the X component, because theta has been stated from the horizontal. Okay, so now we're on 1.10. We're back with this inertia. Now this question, if you look in the memo, has actually got two answers. Okay, so in the grade 11 guidelines, it says to you define inertia as the resistance of an object to any change in its state of motion. So the mass of an object is a quantitative measure of its inertia. So inertia is not your tendency to maintain your mass. And if you are continuing in a state of non-uniform motion, you are accelerating, okay, because uniform motion is constant velocity. So inertia's got nothing to do with acceleration. So the answer in terms of the definition is C, okay, remain at rest or in its state of uniform motion. So that's why if you leave something alone, it doesn't move, or if there's no other forces, it carries on moving at the same velocity. But answer D is also correct, because inertia is the resistance of the object to its change in motion. So an object will want to keep its velocity if you put a force on it that will accelerate it. That property of inertia is not going to change just because you applied a force. It like exists in that particle. So this question was slightly ambiguously phrased, which lets you have C or D as an answer, because the object will tend, see it says the tendency of an object. It will tend to maintain its velocity if you put a force on it, but if the net force is big enough, it will change its motion. Okay, now we've got a person standing on a bathroom scale that's fixed to the floor of the lift. When will the reading on the scale be largest? So we've got the guy pressing down on the scale and the tension in the rope pushing up on the scale. And so then when will you feel heaviest, which is basically when will the reading on the scale be biggest? It's not when you move, nothing at constant speed, okay? For the scale to have a reading that is not your actual weight, the lift has to be accelerating. The moment you are at constant speed, the upward forces and the downward forces are equal. So for anything that's moving at a constant speed, the scale is going to give you your actual weight on the surface of the earth. If you go upwards, which is the correct answer, the scale will give you a larger reading. If you're going upwards and accelerating, which is what increasing speed is, if you are going downwards, the scale is actually like falling away from your feet, and you will appear to weigh less because your weight depends on the force due to gravity. So now it says to you 1.12, which physical quantity is equal to the rate of change of momentum? Remember, Newton's second law in terms of momentum, the net or resultant force acting on an object is equal to the rate of change of momentum of the object in the direction of force. So which physical quantity is equal to the rate of change of momentum? Remember, if this doesn't have rate in, it is wrong. So the answer is C, net force. Now it says to you the gravitational acceleration on the surface of a planet of radius r is g. The gravitational acceleration at a height of 2r above the surface of the planet is. Okay, so we use this to calculate acceleration. G equals g, mass of the planet over the radius of the planet squared. Now, if you look at this question, they're saying to you, what is the gravitational acceleration at a height of 2r above the surface of the planet? We are getting further from the planet. So the moment you are getting further from the planet, the force is weaker. So it works like this. With this law, a big distance is going to give you a small force, okay? So the greater the distance, the smaller the force. So we are going to immediately cross out C and D. Now we are left with A and B, and this is where it gets a little bit interesting. So if we draw the planet, and it says to you the gravitational acceleration on the planet, here is its radius, r. So the gravitational acceleration here is little g. Now it says, what will the gravitational acceleration be at a height 2r above the surface? So if r was the radius of the planet, this is now 2r. But the thing is with this law, you have to find the distance between the two centers. So the two centers are now r plus 2r, which is 3r apart. So if I come here and I substitute 3r into here and I square it, the answer is going to be A, 1/9, because we are timesing 3 squared is 9, so it's going to be 1 over 9r squared. So the g is 9 times smaller, which is the same as multiplying by 1/9. Okay, here we come with the lift again. An object of mass m hangs on the end of a string from the ceiling of a lift cage. The lift is moving upwards at constant speed. If we are at constant speed, my acceleration equals 0. We are in equilibrium. Which one of the following statements regarding the tension in the string is correct? If we are in equilibrium, forces up equal forces down. So the only thing that's going on downwards with this box is my weight, or mg. So if we are in equilibrium, the tension must be equal to mg. Forces up equal forces down. Now it says to you, two hypothetical planets X and Y have the same mass. So here is X of mass m, and here is Y. It says Y, the diameter of Y is twice that of X, so it is bigger. If the acceleration due to gravity on the surface of planet X is g, then the acceleration due to gravity on the surface of Y will be, well, remember this law. This law says if there's a big distance, you will have a small force. So now we're not worried about the mass because the mass is the same. But if we've got a big distance, we're going to have a smaller force. So we're going to rule out g immediately. It can't be the same. It must be smaller. We are left with 3 smaller answers. Remember, this formula says g equals big G m over r squared. So we went from having a radius of r to having a radius of 2r. So now we are dividing here by 1 over 2r all squared, which is the same as 1 over 4, which gives me the answer B, 1/4 of the acceleration due to gravity on the other planet, because it is an inverse square law. So we double the diameter of the planet, which means we decrease the gravitational acceleration by a factor of 4. Now it says to you 1.16, a constant net force acts on a trolley. According to Newton's second law, the acceleration of the trolley is, you just have to know your definitions here. The acceleration is inversely proportional to the mass of the object. Newton's second law, if you want to see it, it's written there at the top of the page here. Okay, we're back to the planets again. The weight of a man on the surface of the Earth is W. Okay, so here is the Earth, and W is equal to your mass times the gravitational acceleration. So the weight of the man on the surface of the Earth is W. Okay, planet X has the same radius. So here is planet X. He's the same size, but half the mass. Okay, this is half the mass. So what will happen if the man goes to planet X? Well, gravitational acceleration, remember his particles are not going to change, is equal to the universal gravitational constant times the mass of the planet divided by the radius squared. This radius is not changing, but the m is being divided by 2 because it's half the mass. So all of the answers that we look at must be the smaller answers. His weight will change because weight and mass are not the same. He can't get heavier. The gravitational acceleration has gotten less, so it must be half his weight. Now it says to you the net resultant force acting on an object is equal to this is Newton's second law stated in terms of momentum. It is equal to the rate of change of momentum. Be careful, this is the change in momentum with time. A is wrong because it's not just the change in momentum, it is the rate of change of momentum. 1.19, a physical quantity that is described as a measure of the resistance of a body to change its motion is inertia. There are a lot of inertia questions in here. Now it says to your car is moving at a constant velocity, so my acceleration equals 0. If there is no acceleration, there cannot be a net force. Which one of the following statements about the forces acting on the car is correct? It looks like straight out the gate, this looks like the first answer is correct. The net force acting on the car is 0. Yes, I like answer A. Why is answer B wrong? There are no forces acting on the car. This is not true. So long as you have the same force forward and the same force backwards, you can still move at constant velocity. The weight of the car is equal to the normal force acting on the car. No, you don't know this because there might be some other force with a vertical component that's not affecting its acceleration but is still existing on the car. There is a non-zero net force. If there is a non-zero net force, that means there is a net force with a magnitude, non-zero, it's got a value. And the moment we've got a net force, we have acceleration, and the question clearly stated constant velocity, so the answer has to be A. Okay, it says the graph below, not drawn to scale, shows the relationship between the gravitational force on a given mass and its distance from the center of the Earth. So this is Newton's law of universal gravitation again, and it boils down to a big distance is going to give you a small force. Okay, it says the magnitude of the force on the mass at a distance r, see here is the distance r, and here is the force F. The magnitude of the force on the mass at a distance r from the center of the Earth is F. Which one of the following is the correct representation of the magnitude of force F, force X, shown on the graph? So here is X, it is a small force, okay? So can you see, if you read this off the graph here, F is at the top, it's got to be bigger, because here is a quarter F, so I need an answer that is smaller than a quarter of F. So clearly A and B are definitely wrong, because I mean just reading off the graph, okay, X is got to be a little number. And then it says to you here, what is the distance from the center of the Earth? It is 6r. So remember, the force equals G m1 m2 over r squared. It is an inverse square law. So if we look at this and we look at it, those are not equal signs. Don't think they're equal signs. We are now making this distance 6r, but the law says we have to square it. So my force is going to change by 6 squared, which is 36r squared. So the force is going to be 36 times smaller, answer D. Now it says to you, net force is a measure of, this is once again testing Newton's second law of motion described in terms of momentum. See up here from the guidelines. If you know your definitions, this one is easy peasy. It is the rate of change of momentum. D, you can't be doing the change in the energy, rate of change in the energy, or change in the momentum. It has to include the word rate. It is the change per unit time. Okay, this one again, 1.23 is know your definitions. Which one of the following forces always acts perpendicular to the surface on which a body is placed? Know your definitions. It is A, the normal force. Friction acts parallel. Gravitation acts towards the center of the earth, and you don't happen to know what the angle of the surface is. And tension needs a rope. It's not to do with a surface, it's got to do with a rope or a chain or some kind of suspended object. Learn your definitions. Two isolated bodies A and B having masses m and 2m respectively are placed a distance r apart. Consider the following statements regarding the gravitational force exerted by the bodies on each other. Now we know F equals G m1 m2 over r squared. So the force exerted by B on body A is half that exerted by A on B. This is not true. This is trying to invoke Newton's third law. And Newton's third law says the force is equal and opposite. You can't have two different values of the force. Yes, I realize the planets have different masses, but their force they exert on each other is equal and opposite. The force exerted on the bodies is independent of the masses of the bodies. Well, clearly not. The formula has got mass 1 and mass 2 in it, so this is also nonsense. We can cross it out. The force exerted on body A by B is equal but opposite to that exerted by body B on body B by A. Yes, that is a correct statement of Newton's third law. The forces will always be attractive. Yes, this is also in the law of universal gravitation. So I've got 3 and 4. 3 and 4 only gives you answer C. We are nearly at the end now. 1.25. A net force F, which acts on a body of mass m, causes an acceleration a. Yes, F net equals ma. If the same net force is applied to a body of 2m, the acceleration of the body, well, if you think of this in numbers and say 4 equals ma, the same force is going to be 4. How would I make this bigger? Then this is going to have to decrease. My acceleration is going to have to decrease by a half, because 2 times a half is going to give me exactly the same value here. Yes? So look here. If this was 1, then A would be, let me do this nicely here, okay? Let's say F net equals ma. So you can take a hypothetical value. So initially, let's say the net force was 4 and my object's mass was 1m, then the acceleration would be 4a, okay? If I now say to you the same net force is 4, but my object is 2m, what do I have to do to this 4a to make this equation equal? I have to go 4 divided by 2, which is a half a, to give me the same answer. Of course, you could always just use the second law, because the acceleration is inversely proportional to the mass. So if we increase the mass, the acceleration is going to decrease. So all of the decreasing answers have to be the correct ones. Okay, 2 objects of masses 2m and m are arranged as the diagram below. Which one of the changes will produce the greatest increase in gravitational force? So the formula says F equals G m1 m2 over r squared. So to get a big force, according to this law, we need a big mass, and the other way to get a big force is to put the objects close together and put a small distance between them. Okay, but now this one goes by the product and this one goes by the inverse squared. So any change to the distance is going to have a bigger change on the force than a change to the mass. Okay, look here, if we double the larger mass, all we're doing here is timesing this by 2. If we halve the smaller mass, we were going to decrease it, so this one is definitely not going to work because a smaller mass gives you a smaller force, so we don't want to do that. If we double the distance, a big distance gives us a small force, so these two are blatantly wrong. But if we halve the distance between the masses, it's 1 over 2 squared. So this, and remember we are dividing by a half squared, so if you divide by 1/4, it's the same as multiplying by 4 over 1. So halving the distance will give you a 4-fold increase in the force, so the answer is D. According to Newton's second law of motion, the acceleration of an object is independent of its mass. No, what nonsense. Equal to the mass, not what nonsense. It is D, learn your definitions, inversely proportional to its mass. Okay, 1.28, the diagram below shows 3 blocks P, Q, and R suspended from a ceiling. The blocks are identical, stationary, and have the same mass but are at different heights above the ground. The connecting strings are massless and inextensible. The tensions in the strings are what? Okay, so now the free body diagram for this, all of them, is going to be equal to the weight, mg, and the tension upwards. Okay, but it says to you they are identical and have the same mass. So this is m, this is m, this is m. So the weight downwards on all of them is going to be mg, mg, mg. So which of the statements about the tension is correct? There are only 2 forces here, the tension up and the weight downwards. The tensions have to all be the same. Remember, tension in the string is the same throughout. It really doesn't matter how long the string is. The only way you could possibly get this to matter is if you, for instance, had an 8-kilometer long string and then somehow you had suspended it like one of these really 8 kilometers above the surface of the earth and managed to affect little g, but you're never going to manage to affect little g. So the tension in all of the strings is the same because the only 2 forces are the tension upwards and the weight downwards, and the weight is identical for all 3 of the objects as per the question. Now it says to you, a constant horizontal force F is applied to a box resting on a horizontal frictionless surface. Well, if there's no friction, the box is going to want to move. Which one of the following statements regarding force F is correct? Force F will cause the box to move with not constant velocity, it's going to accelerate it, not constant kinetic energy, because if you have a net force, you will accelerate, and if you will accelerate, your velocity keeps changing. That's the definition of acceleration, so your kinetic energy has to change. And constant momentum, no, because momentum is mv, and if we have a force, it causes acceleration, and then vi and vf are always different. So the answer is A. And we come to the last question, which I think is from 2020. These questions are close to the ones from 2020. The last 2 are at least. It says a block rests on a table, the table's on the concrete floor. The normal force is represented by N as shown in the diagram below. Which one of the following forces will form an action-reaction pair with the normal force? Now, an action-reaction pair needs two objects, okay? So the normal force is the force of the surface of the table on the object, yeah? So we need something that's got the surface of the table and the block, because it's not the force of the earth on the block. That's your weight. And then remember, if you ever use Newton's third law, you have to have the same two objects, but you switch them around. The force of John on the car, the force of the car on John. So if we want the force of the block on the earth, that is not what the definition of the normal force is. The normal is a force that occurs perpendicular to a surface. So you need the object and the surface. So this one, C, has got the table surface, but that is actually the normal force, okay? So the table surface on the block looks promising. Okay, the block on the concrete floor is definitely wrong. But this is the normal force is equal to the force of the surface of the table on the object. So we need the force of the block on the table. That is the one that is equal and opposite with the same two objects, but in the opposite direction. Now this one again wants you to know Newton's second law in terms of momentum. As stated in the guidelines, learn your definitions. The rate of change of momentum of an object is equal to B, the net force acting on the object. Learn your definitions. Now it says to you, the gravitational acceleration on the surface of planet X with a mass m and radius r is g. So, okay, let's draw this. Here is planet X with a mass m and radius r. The gravitational acceleration on the surface of planet Y, here's planet Y, it says the radius is half r. So it is a small planet, but it is awful heavy because the mass is 2m. Now, let's think about this before we even look at the answers. The force is equal to g m1 m2 over r squared. So to get a big force, we need a big mass, okay? And to get a big force, we also need a small distance. So check this planet Y, yeah? It is heavier, so this is increasing the force times 2. And it is smaller, so this is increasing the force by a half squared 4 times, yes, because a half times a half is a quarter, and if you divide by a quarter, it's the same as multiplying by 4. So according to me, 4 times 2 is 8. The acceleration due to gravity is going to be d8g. It cannot be smaller, because the moment the planet got smaller, the gravitational acceleration got bigger. The moment the planet got heavier, the gravitational acceleration got bigger. And then you have to remember that the radius effect is squared, so the answer is D.